So this is the third part of this mini-series on measurement-based quantum computation. And today, we are changing gears a little bit. So we are talking about computational phases of quantum matter, and this is hopefully fun stuff. In the last two lectures, we did the things that were not dispensable. We talked about universality, and if you want to investigate the computational model, you make better sure that it is universal. You also want to make sure that it is fault tolerant. Yeah? If either of those two things does not check out, that would be a huge detriment. So you want to make those things sure, but then you're done kind of with the necessary things, and then you can explore. And we will do that today. And so let me show you a little bit what these, I will not talk about all these things, but what there is to explore. So experiments I spoke a little bit about. Fault tolerance we covered in the last class. But there's more fun stuff. So we have the connection to foundations of quantum mechanics. Who recognizes this picture, by the way? Can you seen this before? I have not seen it before. Okay, so this is no hand. I see no hand. So this is kind of in the corner of the Bell inequalities. It is precisely Cauchy-Specker's original proof of contextuality of quantum mechanics. And we have a connection to contextuality of quantum mechanics for measurement-based quantum computation. So every measurement-based quantum computation that computes a not too simple function is contextual. But I will not talk about that at all today. I just give you an idea of what is out there to explore. Then also there is profound connections to graph theory. So this is mostly work by Martin van den Nest and collaborators. So there is measures of complexity formulated in terms of graph theory, specifically tree width and such things. I just want to point it out. I will also not go into this in detail. I will talk about something else called computational phases of quantum matter. But before I go there, I want to make a general comment. So I want to take you back to a conversation that we had in Anthony Leverrier's first lecture. Yeah? So in fact, I asked the question, and he responded, and then Victor Albert joined the conversation. So Anthony pointed out that what he was talking about is improving codes of this type to codes of that type. Yeah? Making them linear in the distance. And I asked him, this code already gives you a threshold, a non-zero threshold in all likelihood. So why are you going from here? What's the point? And his response was essentially, come on, we are coding theorists. We provide the best possible code. Call it a game if you like. Call it a game if you like. That was his response, upon which Victor Albert got up and said, no. Don't need to go there. Yes, both have a threshold, but the threshold value will be higher here. And the threshold value matters. The higher the threshold, the less the constraints on the experimentalists. So it's actually practically useful to go from here to here. Okay, so why am I bringing this up at all? The reason I'm bringing it up is you already see from this, and this applies to coding theorists, it applies to people like me, applies to many people in this room. We are operating in this twilight zone between fun and utility. This will apply to many of us, and also applies to the material that you see on the slide. This is fun, but it is also useful. These things are also fun. The usefulness is maybe less clear, but there's a point. There is a reason why we are looking at all of these things. And the reason is that we want to find material to construct quantum algorithms from. So this is our basic idea. We have somehow the impression that there's only a very few quantum algorithms around, and we want to bring in more fundamental ideas to the field. Maybe that helps with the construction techniques for quantum algorithms. So this is our motivation. Just wanted to say that. Okay, so now without further ado, let's get started. Okay. So what you see, yeah, I wanted to say that. This was one of the two things I will explain today. So what you see here is a stylized phase diagram of water. You have the temperature axis from here to here. So this is freezing, this is boiling, and you have the pressure axis from here to there, low pressure, high pressure. Yeah, but you see, I mean, okay, it's a phase diagram of water. It's all the liquid phase here. And normally the physicist, what would the physicist think about in terms of phases? Simple properties continuously varying, like density and viscosity and stuff like that. But there's also a very complex property, life. Yeah? Life happens all in the liquid phase of water, really in all the corners. Boiling, freezing, high pressure, low pressure, moderate conditions, everywhere in the liquid phase you find life. Okay, that is not the phase of our interest, it's not the property of our interest, but it is a complex property that a phase of matter shows. What we are interested in is computational phases of quantum matter. So we will be talking, as it will later turn out, phases that are symmetric under some symmetry group, or Hamiltonians that are symmetric under a symmetry group, and then their ground states. So everything here, our phases are all at temperature 0, and symmetry, as it turns out, matters. And then, yeah, so a computational phases per definition is a phase of ground states. You vary a Hamiltonian, look at the ground states, and then you reach a phase boundary at some point, and this is where your phase ends. And we look at phases, physical phases of ground state that have uniform computational power. So that's just the definition for now, but such phases actually exist. We have examples of those, and for all the examples that we know, one requires symmetry. So symmetry is a very important ingredient. So the phases that we are talking about are symmetry-protected topological phases. Okay, so let me, yes? Oh yeah, thank you very much. I almost forgot to say. So we are using, you have a bunch of ground states that span the phase, that are in the phase. Yeah, the phase is a collection of ground states. And each of these states can be a resource for measurement-based quantum computation. Sorry, thank you very much. I forgot to say, yeah, so this is how we're using the states. We are using the states as resources for measurement-based quantum computation. And then you can pick different states in the phase, and so you might think, oh, some may be useful, some might not be useful for quantum computation, but it turns out every state in the phase has the same computational power. You can do exactly the same things with it. In the sense of computability. So sometimes you have a computationally universal phase, so you can do everything that a quantum computer can do with any state in that phase. Sometimes you have less power than universal. So for example, we will be looking at one-dimensional phases, then you can be 1-qubit universal, 2-qubit universal, you can have less. Yeah, so the power differs from phase to phase, but it's constant across the phase. So what you can compute in it is constant across the phase. But since you mentioned, so the efficiency will vary across the phase. So if you are in the center of the phase, it is the easiest to compute. If you're moving towards the phase boundary, it becomes harder to compute. But still, with a multiplicative overhead factor, you can still compute the same things. Good, okay, and we'll get to that. Yes, I will give you examples. Although, yes, I will give you examples. Mm-hmm. Good. So yeah. So really, what we are talking, symmetry is important. So what we are talking about is symmetry-protected topological order. So I just want to quickly introduce the concept. I think there's many condensed matter physicists here in the room, and so for them the concept will be clear. But let me mention it anyway. So this is about ground states of Hamiltonians. And so the first thing to say is that the Hamiltonians are symmetric. So we have a symmetry group. If you conjugate the Hamiltonian under the symmetry group elements, the Hamiltonian will remain unchanged. Okay? Symmetric Hamiltonians. And then what else is there to say? So yeah. So now this is the parameter space for the ground states. We also assume that the ground state of these Hamiltonians is unique. So the ground state shares the symmetry. Yeah, and so then we look at two particular ground states for different parameters, all symmetric. And now are we asking, are these two ground states in the same phase? And the condition is, we must have a path in this parameter space between the two ground states so that every ground state on the path has the same symmetry, and the energy gap above the ground state never closes. Energy gap above the ground state never closes. So an energy gap closing is an indication of passing a phase transition. Yeah? And if this doesn't happen, then we are in the same phase. Good. So this is a completely standard condensed matter definition of phase. Yes?
Can you just have a condition around that? Can you change the symmetry without closing the gap?
We do not want to change the symmetry. I mean, the symmetry the symmetry applies to the entire parameter space. So the symmetry is never changed. Yeah? But you have, the symmetry can be realized in different ways. So for example, let me give you an example. So this is actually the example that we will work with. So let's consider a system of qubits. And we have a symmetry group Z2 times Z2. Just to be concrete, I elaborate this example later. And so it is generated by the two operators. So these are tensor products of Pauli spin flip sigma x and identity alternating. Yeah? And so this can be on a chain, on a ring. Yeah, it just goes on like that. So this is the first generator, and the second generator is, excuse me, the second generator is the same thing displaced. Okay? So then I give you now two states that are in very... What's the difference is the displacement. So this is qubit number 1, qubit number 2, number 3, and so forth. This is qubit number 1, number 2, number 3, and so forth. And you see this generator has axis on the odd qubits, and this one has axis on the even qubits. Yeah? Okay, so I think it's, please absorb it. We'll talk a lot about that symmetry. So this is basically our example for today. Yeah? Okay, so let me just give you two states that are invariant under the symmetry. The first is the cluster state on a line or on a ring. Yeah. I hope you can see that. The way to see it, one way of seeing it is that these symmetries are actually in the stabilizers. So if you, okay, so remember what the cluster states stabilizers look like on the line. You have this one, this one, this one. And so we see, stabilizer is a group, so we can multiply them, and you see modulo what happens on the boundary. So for safety, let's be on a ring, but you see that we get these strings. So the symmetry is in the stabilizer, and so it fixes the state. So this is a symmetric state. The tensor product of all spins pointing up in the x direction is also invariant under this symmetry. That's another state. So we have, and we will later see that these two states belong to different phases. So this is a trivial state, it's completely unentangled. This state is entangled, short-range entangled. So you see both states are symmetric, but they are different, and they will turn out to lie in different phases. And we will talk about that shortly. So the first condition, I mean, if you want to satisfy the second condition, you have to define what your path is, you know? Yeah, so and what do you imagine for the path that is less than what is explained in point 1?
Change the group from the interesting group to the trivial group. That's what happens.
Yeah, exactly. And when you go to the trivial group, that is, you do not enforce symmetry, then all of this falls apart. Yeah, so the phases become bigger, and without symmetry, the same discussion without symmetry, then these two states would actually be in the same phase. So symmetry is very important for our discussion. Good. Okay, so much about symmetry-protected topological order. Finally, after hopefully not half of my talk, session share, how far? Whew, let's race. Okay. You're finally halfway into my talk. Almost, I'm getting to the outline. So this is what I want to tell you today. Yeah, I want to explain more this concept of computational phases of matter. I want to motivate it. I want to give you two motivations and a short history of the question. So I want to tell you about kind of reference points in this field. And then very, very briefly, I want to mention computational universality as I was asked about. So I show you a computationally universal phase of matter in 2 dimensions. But all of this will be very sketchy. Today it's more of an outlook lecture. I would just want to interest you in the subject, and maybe then you will read up about it if you're so inclined. Okay, so here comes my motivation. So why are we looking at this at all? And so we know, that symmetry considerations are very useful in particle physics. Elementary particles are classified by symmetry. Does the same hold for schemes of measurement-based quantum computation? Does symmetry apply here too? It's a question that we can ask. And in fact, well, it is the case. We do not understand the answer to this fully, but we know quite a bit about this question. We know quite a bit about it. And suppose we could resolve it fully, and then we want, as I already said, we want to take it to algorithms. Yeah? So our real question is, what does symmetry tell us about quantum algorithms? Does it give us an approach to design quantum algorithms? About this question, we know very little at this moment. We know a few things, but very little at this point. But this is what we really want to answer. This is why we are doing this. There's another motivation. If this is too lofty, here's another motivation that I'd like to give. So we can ask the question of how rare resource states for measurement-based quantum computation are in Hilbert space. You know, how do we know whether a state is a good resource or not? Yeah, and so there's an interesting observation made by David Gross and Steve Lamia and Jens Eisert. So they realized that only the tiniest fraction of quantum states in Hilbert space, measured by the Haar measure, only the tiniest fraction can possibly be useful for quantum computation. And also interesting is that the majority of the states, namely those that are not useful, are too entangled to be useful. Maybe an interesting counterpoint to the entanglement as resource perspective. Okay, so now that we know that, we could ask whether symmetry changes the picture. And it does indeed change the picture. Because, you know, as I said, if we are if we are in the presence of symmetry, then our parameter space of available states, it becomes like a map. There are all these countries or all these phases that offer computational power. And if you find one phase that has a lot of computational power, then computational power is no longer rare because you have it in an entire phase. Okay, so symmetry changes that setting. Okay, good. So let's get started. I want to, yes, it's probably my midway point. But there's really only one thing today that I will explain at the technical level. So I think I'm doing okay. Good, so here's a short history of the subject. The subject was started by Akimasa Miyake when he was a postdoc at the Perimeter Institute. So he realized that symmetry protects quantum computation. So he considered a hybrid between measurement-based quantum computation and adiabatic computation. Let me sketch that briefly. So what he considered was a spin chain, something like this. And yeah, he considered the ground state of some Hamiltonian for that spin chain as a computational resource. And he figured out that the details of the Hamiltonian didn't really matter. What mattered was the symmetry. So symmetry protected the computation. So the ground state would be used as the computational resource for measurement-based quantum computation. However, there was this adiabatic element in it. And it was that when a spin was about to be measured, the coupling was adiabatically tuned off. The coupling to the remainder of the chain, not only thereafter that qubit was measured. Okay? So this was a hybrid adiabatic MBQC scheme. And the important thing is that the computation was guaranteed by the presence of the symmetry. You didn't need to know any details of the Hamiltonians or any details of the ground state. As long as the symmetry was present, also Z2 or Z2 symmetry, then you could compute. And Miyake realized that this is related to symmetry-protected topological order in condensed matter physics. So this paper, I would say, is the birth of all these considerations. Next piece of work, and this is what I actually want to explain at a tiny bit of a technical level. So, yes? Mm-hmm.
How do I implement all your circuits in such a one-dimensional system?
You don't. So yes, this is a very important point. So most of what I will say today happens in one dimension. And in one dimension is really a toy system, because we know that we have this relation between the circuit model and measurement-based, that measurement-based is always one dimension higher up than the corresponding circuit model. So a one-dimensional MBQC maps to a zero-dimensional circuit model. So you have a finite number of qubits, like one or two logical qubits, or 3 or 4, finite number. And that is, of course, not good for universality. So yes, I will go to 2 dimensions, but only at the end of the talk. So these first works, they were all done in 1 dimension. And really, this is just a toy situation, but 1 dimension is much easier to handle than higher dimensions. So this is where the work started out. Yeah, and no chance, it's not even quite true. Little chance with a caveat for universality in 1 dimension. Yeah, but it's a laboratory that we can build on. Good. Okay, so let me talk about this second waymark. This is by Dominic Els and the group at Sydney, Andrew Doherty, Stephen Bartlett. Okay, so compared to the previous work, this was one step forward and one step back. The step forward was that this is now about measurement-based schemes directly without any adiabatic component. And the step backward is that this is no longer about computation, not even on a bounded number of logical qubits, but this is only transmission of quantum information. So this is a much simpler protocol. However, this, on a technical level, this paper proved to be very important because it imported math, namely group cohomology, that condensed matter physicists had already found to apply to their considerations of symmetry-protected topological order. Yeah, these people imported this to the field of quantum information. And kind of this DNA of group cohomology has remained in all the subsequent works on the field, and that's why I think I would like to explain it to you a little bit. Okay, so this is what condensed matter physicists had found out. So given you have a system that's invariant under a symmetry group in one spatial dimension, the symmetry-protected topological phases are classified by what's called a co-cycle equivalence class, omega in brackets, in group cohomology. And the one technical thing that I want to do here in this talk today is I want to explain to you what this is. Yeah? Good. So the condensed matter physicists had figured it out. You have the references here. And the group in Sydney imported this into quantum information and then they made something out of it. For concreteness, before I go into the explanation what this co-cycle is, let's have a concrete model in mind. So you see, so this is the Hamiltonian. We have a parameter in there that we can tune, and you see what this Hamiltonian is. It's the cluster Hamiltonian. You see the cluster stabilizes here in the presence of a magnetic field. And now we vary the relative strength. So when alpha is 0, then the ground state is a cluster state. When alpha is pi over 2, this term disappears, and the ground state is just kind of all spins pointing in the x direction. So this is the states I previously had on the board. And now by varying alpha continuously, we can interpolate between the two states. And actually, there's a phase transition in the middle. So we can define, so the symmetry is what I previously showed on the board. You can check explicitly that this Hamiltonian is invariant under the symmetries and an easy exercise. Okay, and then we can measure what's called the string order parameter. It looks roughly like the symmetries, only that it has a finite extent, large but finite extent, and then it is terminated at the endpoints, and you have the identity to the left and the identity to the far right. This is the support of the string order parameter. Yeah, so you measure it and you find that the string order parameter starts out at 1 at the cluster point, then the value remains high, and then at the midpoint here, it goes to 0. So these are finite size simulations, so this drop is smoothed out a little bit, but if you could simulate very long chains, you would just get a vertical drop here. So that's the point of the phase transition. Okay, so we have two phases now, and these phases are labeled by these co-cycles in group cohomology that I mentioned. So let me explain to you what this co-cycle is. Okay, so I need to talk a little bit about the MPS representation of quantum states and of measurement-based quantum computation. Okay, so I talked to a few over breakfast who are using tensor networks for their work, but how many here in the room are familiar with matrix product states and tensor networks? Okay, thank you very much. It's a few, but less than half. So let me just quickly go through it. So we look at the simplest of tensor networks, which are the matrix product states suitable for dimension 1. Okay, so what we can do is we take a general quantum state and expand it in a local basis, say the computational basis, so that we get amplitudes. Now, we can make an ansatz for these amplitudes of this form, and it turns out to be useful for describing one-dimensional systems in condensed matter. So what is it? So we are having this ansatz that the amplitude for a particular basis state is of this form. Yeah? So it is a bunch of matrices multiplied, one matrix for each site, depending on the corresponding basis state. Yeah? And then the trace taken over this expression. Okay, so this is an ansatz, a useful ansatz for quantum states that occur in nature. Okay, so these are D by D matrices, and D is called the bond dimension. Huh? Graphically, if you draw it as a tensor network, it looks like this. So at every site, you have these tensors. So they have two legs that we call vertical legs. That is why we can multiply them as matrices. And then they have another leg for the physical label, yeah? for the label of the basis state for the physical state. So this is the physical leg. These are called virtual legs. And they are contracted. Okay. Measurement-based quantum computation can be represented in this picture. So namely, we know that in measurement-based quantum computation, we measure each site one by one in a certain basis. So we're now thinking about this object. So the tensor, the MPS tensor, with the physical leg contracted by measurement. And so two legs remain. And this can now be a gate. This can now be a gate acting on virtual space. So it doesn't have to be unitary. I mean, you have to choose your basis carefully such that this is a unitary transformation, but this can be done. And yeah, so this is what is called quantum computation in virtual space or correlation space. So here you have your chain again, and here is where your virtual quantum register lives. And all these blocks are transformations of the quantum system on the virtual quantum register. Good. So this is something that I will later refer to. Okay, so now let's talk about symmetry again. So this is a result that has been found that whenever we are dealing with states that are symmetric, then the tensors themselves must be symmetric. And this is how the symmetry acts. So this is the symmetry action on the physical leg, and this is equivalent to symmetry action on the virtual legs. So I will not prove this, but just to get some idea of what this relation signifies, let us prove one direction. So let us show that if this relation for the tensors hold, then the state is really symmetric. That's the easy direction. So let me just do that here. Okay, so we have a tensor here. So this, okay, represents the quantum state, and we have now the symmetry action acting on each of these sites. Okay, so then I'm using this equivalence. Okay, I'm pushing the symmetry to the virtual legs. Okay, I hear that there's maybe questions. Okay, and so you see, what we are getting here is cancellation. Okay, and so of course this continues, and so on the virtual legs, the symmetry actions always cancel, and so we're getting something of this form. Okay, so you see this, it's the same state, and it's invariant under the symmetry action. So that was the easy direction. If this holds, the state is symmetric. under the symmetry action. The complicated direction is the other one, and I'm not going to show it to you. I just wanted you to become a little bit familiar with what this relation means. Okay, so the important thing now is that V is not a linear representation of the symmetry group. Yes? For now, in the end, it turns out that we don't have to, but for now, let's assume it. Yeah? Let's assume everything that makes our life simple. Okay, so V is what's called a projective representation of the symmetry group. So if this was a linear representation, the relation would look the same, except that the phase would not be here. Okay. And so think about the Pauli operators, for example. The Pauli operators are a projective representation of the group Z2 times Z2. So the group Z2 times Z2 is abelian. The multiplication of Pauli operators is not abelian, so you know that there will be phases. Okay. All right, and so let's give those phases a name. So let's call these phases omega, and they depend, of course, on the group elements. Yeah? So this is, remember, our group co-cycle had an omega in it. So this is going to be important for our discussion. And also, yeah, so remember this relation. Also remember, or also please note, that the symmetry action here on the right is independent on the phases we choose for these projective representations. We can redefine the phase without having an impact over here, because the phases here and here cancel by complex conjugation. Okay, so this phase is basically arbitrary. Good. Now, so I don't want to lecture you on group cohomology, but if you check the definitions, you find that omega, just by what we said, is a two-co chain in group cohomology. And then if you check the definitions further, obviously by associativity of matrix multiplication, this must be equal to this. We're just putting the brackets differently. But that has a meaning for these omegas, because these omegas appear in those multiplications. So this gives you a constraint on the omegas, and if you work it out, this makes it a two-co cycle. So we're dealing with a two-co cycle, which is a topological object. Final point, and I already said this, the symmetry action is invariant under these transformations. And again, these transformations have an impact on what omega looks like. Yeah? If I redefine these projective representations here, the phase will change. Okay. And so, but this is an equivalence transformation, really. Yeah? So you can use this, you can use that, they are equally good. And so we have equivalence classes of these phases omega of this form. And it turns out, so this is now what condensed matter physicists have found out, that these equivalence classes characterize symmetry-protected topological phases. Good, so I just wanted to tell you, maybe this was a little bit of math here, but I just wanted to tell you what the object is. And this is interesting because there's all sorts of mess going on in these 1D SPT phases. The states are not the same, they're very different. But what matters about these phases is all contained in this tiny algebraic object. Yeah? Good. So here's the example of the Pauli observables. I said the Pauli operators form a projective representation of the group Z2 cross Z2. Good. So now if we go to our cluster chain example again, so then we find two phases. One is non-trivial and one is trivial. And the non-trivial one is characterized by this projective representation of Z2 cross Z2 that is the Pauli observables. Okay? Good. So now finally, after all of this, I can tell you what the Australians did. So they thought about this object here. So this is now the MPS tensor contracted with a state in the symmetry respecting basis, in the X space. So that matters. It's only valid for this basis. And so they showed that this tensor must decompose as a tensor product, or this matrix must decompose as a tensor product where one factor is a Pauli operator and the other is called junk. So you can say nothing about this. You can say nothing about this. Okay? But the interesting thing is that this Pauli operator is constant across the phase. It's the same everywhere in the phase diagram, or in that particular phase, whereas this operator down here may change. But they are in a tensor product. And so so the way this is useful is that you can use this as a logical subsystem and just never think about it. And so in this subsystem, you can have computational wire. So the identity gate, basically, you can shuttle information across the chain, from left to right. And that would be stable. That property would be stable across the entire phase. Okay, so this is the result of Els and company. Questions?
But this seems like a classification of only of MPS space, not general space.
Yes, this is true. But in gap phases in one dimension, gap states in one dimension are well approximated by MPS states. Yeah, but thanks for asking. So we have been working recently on separating the computational phase of matter discussion from MPS. So our new work bypasses the MPS framework. Good. Okay. Whew. All right then. Yeah, good. Let me just say this is what they did, and this is how they employed this cohomological framework. Let me speed up, but let me say one point about their work. So they realized the difficulty to extending this to computation. I mean, we don't want to only shuttle information, we want to compute. And they realized that this nice tensor product relation applies only if you measure in the symmetry respecting basis. And then you get wire. But we want to do more. We want to compute. And since the symmetry respecting basis only gives us wire, we need to move away. We need to move to other bases. And then, well, the factorization property goes out the window. Yeah? So if you measure in a general basis, you will now have a linear combination of various such terms. The junk tensor or the junk matrix is always different. And so the tensor factorization goes out the window. And so what this physically means, or from the viewpoint of quantum computation, is that you get logical decoherence into your logical subsystem, which is bad. So this is the main problem of generalizing this to computation. But this problem has been overcome. That would be a different talk, but I tell you, this was the main problem in thinking about how to compute in these systems and has been overcome. Good. So, okay, so this is what I wanted to say about that piece of work. It's the only technical portion of my talk, and so let me just continue with what happened afterwards. So here, Miller and Miyake is the first group of people who actually overcame this problem. Yeah? So they discussed the first one-qubit universal scheme of measurement-based quantum computation, where you had the computation in the entire phase. And then, as a follow-up of this, work from our group, and means what? I'm done? I'm over? Is my time up? My time is up. Oh dear. Can I have a 2-minute extension? Okay, thank you very much. So, okay, so this is about classification of measurement-based quantum computation. So we now showed that computational phases of matter is generic. We have what we call the SPT to MBQC meat grinder. And so you put in the symmetry group, that co-cycle equivalence class that I spent so much time telling you about. Now hopefully it pays off. You put in this information, algebraic information, and out comes a scheme of measurement-based quantum computation. So we have a classification result of MBQC schemes in 1 dimension. In my remaining 30 seconds, let me just say, you can go to a dimension 2 and think about a computationally universal scheme. Yeah? So we have a few computationally universal phases in 2 dimensions. Symmetry look a little bit different. Yeah? So they are now on lines. Symmetry act on lines, and you have all the translates of that symmetry as well. So on and so forth. I cannot go into the detail, but I want to tell you a little bit about the techniques used. So now we have symmetries that look like this, but we are now 1 dimension higher up, so the tensors have 5 legs. And part of this technically is symmetry Lego. And I want to show you one final thing, and this is that. Okay? So remember when I did my first lecture on measurement-based quantum computation, I showed you the identity gate. That's the first thing I showed you. So here's now what the identity gate looks like in this computational phase of matter in 2 dimensions. Yeah? So it's a bunch of symmetry constraints put together. You know, I do not have the time to explain it, but I just want to make you curious. Good. Okay. So let me summarize. So I have given you an introduction into computational phases of quantum matter. Some of these phases are universal. So in 2 dimensions, you can have a universal such phase, or a few of them. And at the technical level, we play symmetry Lego. And I think that's fun, and I would like to recommend it. So if you're interested, you may consult these papers over here. Thank you.
Wonderful experience. Any questions? You also try with the very DPA.
Mm-hmm.
Why is it measurement based?
Why is what relevant to measurement based?
To measurement based computation, not calculation
Okay. I'm not saying it's not relevant for other models of computation, but measurement-based quantum computation has allowed us to make an inroads. Yeah, so it has given us the way to get into the matter and probe it.
I have one question.
Mm-hmm.
Does the symmetry at the beginning rich enough? Or you don't have any symmetry group?
Has to be rich enough. For what we know, it has to be rich enough, and you see it in 2 dimensions. I didn't talk much about it, but the symmetry group here is larger. Yeah? So this is a Z2 by itself, this is a Z2 by itself, but then you have all the translates. And so you get a larger symmetry group, and for as far as we know, we need that. So not every, we do care, not every symmetry would give you a computational phase of matter. Provably.